So, okay, welcome back everyone. Now let's resume Misao's lecture. So
Okay.
we even going further and bring us the cosmic answer, right? About something.
Okay.
So let's continue.
All right. Thank you. So now, I'm going to talk on some nonlinear delta for well, it's essentially talking about some examples. I mean, to show how you compute them and so on and so forth. The first example will be the case where which is given like this: that it's you have a multiple components of scalar field, but all are essentially slow rolling, so that a number of e-fold will be just function of the field configuration. In this case, of course, you can easily, once you know the how the number of e-fold depends on those scalar field, which you can compute from some solving the background equations of motion, then you can easily compute the delta n in terms of these fluctuations that all these are essentially evaluated, should be evaluated on a flat slice at the horizon crossing. And in many cases, these can be, if they are all slow rolling, they can be approximately evaluated very easily. I mean, like h over 2 pi and so on and so forth. Anyway, this delta phi would contain all the necessary, say, quantum fluctuation information. It may have some non-trivial non-Gaussianity, non-trivial 3-point function, 4-point function, but delta n formula is essentially independent from those statistical nature of the delta phi. But it just gives you these expressions. Okay, and then so this is a very simple example, which I thought it was kind of a pedagogical example of how to use this delta formalism for some multi-component scalar field. The assumption is like this: assume that you have some inflaton field, and later I just consider some two field. And then there's some field which controls the length of inflation and everything. This is in the case you have just single inflaton field. This is called hybrid inflation, and in the case of hybrid inflation, the chi determines the end of inflation, and as soon which makes this inflaton trajectory unstable and end the inflation. So in the Lagrangian, essentially this is just a kind of a parameter field. So it doesn't contribute to the number of e-folds. So for simplicity, you just assume that this just fixes the end of inflation, say, surface in this field space. So for example, you have some phi direction, which is this n component direction, and at certain point, when it reaches certain point, inflation suddenly ends, and they hit the universe. So this dotted sort of a curve, and this curve will be the in model presented here in this Lagrangian and potential, but this potential is in some sense destabilized here, and you will have something due to this chi field. But in the language of delta n, this doesn't contribute because it just fixed the end of inflation stage. Okay. Now, assuming this, assuming for simplicity, just you assume that this is a sort of a can be written as essentially this means that it's a product of the potential. So if it of the each component, and if this can be written, the potential can be written as a product of potential of each component, and if you exponentiate it, then it's in the exponential argument that then you will have just sum of some functions of each scalar field. So in this approximation, things becomes easy because the slow equation motion is just in terms of the number of efforts, but it's just going backwards in time. So you're actually solving equation backward in this direction. Will be just given by this 3h over d phi d dv d phi a. And if this is just a product, and then an h square will be just given by the potential. So this is just the derivative of v with respect to phi a divided by v. And in the then it's, if this is product, and then the other component just cancel each other, and you only have one function of a, which determines how phi evolves. So this makes the equation easy to solve. That's just, I mean, this is as I said, pedagogical model, which is nothing to do with reality or anything, but which to show the how you can compute the then, and so if you make the potential too complicated, then you lose what you're doing. So let me just example. For example, so choose this example. So if you choose this example, then as you could easily see, then as a function of n, you can easily solve each of the scalar field model, and so this means that you have some specific you can easily integrate, as you could see that if you multiply both sides by dn, you immediately get n is the integral of this d phi over u prime. Yes. So for each variable, you just introduce new variable qa. This is just change of a variable. Then this means that you have this d log qa dn equal 1, and which actually means in the simplest case that if you have n component and so each field has some directional in some sense cosines in this field space. That's the direction of motion. Then altogether, this means that you have two equations. One is that when the universe evolves, this in some sense radial direction will evolve in proportion to n, while this angular direction just stays constant. So this actually means that this direction, angular, sort of orthogonal direction, orthogonal to the trajectory, will be so-called isocurvature direction. But anyways, so in general, because this you cannot really explicitly decompose them into this formula, but in this simplest case, you can do this. So for example, in the for two field case, then you can just use the say scalar field into two components. One to the radial decomposition. So q1 is q cosine theta, q2 is q sine theta. Then this equation motion implies that theta will be a constant. So this will be a kind of a trajectory you would have. Okay, so you have the q1 space, q2 space. This corresponds as phi1 and phi2. And then in this coordinate q1, q2, all the trajectory with the radial. Okay. So, and the theta is just a concept. I mean, so which means that the theta defines the difference between different coordinates. I mean, sorry, the trajectory. So and this automatically implies that you can write down the number of efforts, which is essentially given by a log of this radial direction q. But if for some reason you have the final sort of a condition for this the end of inflation, for example, is determined, for example, by some in two-dimensional space, some how to say, the line or the curve, which is given by some function of theta, then you will have this theta dependence at the end. And this is exactly the same as maybe I should I don't know if I can. I don't know how to. Is there any way to just a minute? Go back. Well, I don't know if you remember. I draw a diagram, a case of several cases of delta n, and one which I draw like this, two lines, and but the end of inflation will be like this, and then this merges together to one, something like this, and depending on how the inflation ends. In the beginning, you have this isocurvature direction, which doesn't really affect anything. But if the end inflation is controlled by some sort of a hypersurface, which does depends on this, in our case here, this is the theta direction, depends on theta, then this dependence appears in the final result. So again, this means it's sort of useless to compute the evolution of the curvature perturbation during inflation, because everything is essentially determined at the final slice. Final slice. And as you can see, so the only dependence in this case on this isocurvature direction, or some direction of constant of motion, appears appears through the final condition. Okay, and this is a quite it's a very similar thing can happen to many interesting scenarios. For example, there are some so-called moderate reheating scenarios and so on, and then this theta will be the parameter of modulation. Maybe this theta may be something to do with the baryon number and so on and so forth. So in that case, you can also introduce some non-trivial baryon number perturbation and so on and so forth. But anyway, so in terms of number of E4, this is the sort of expression you will obtain from solving this background equations of motion. Then once you have this, then it's very trivial or easy to just compute delta n. You just make fluctuations in Q and fluctuations in theta. And these are the sort of initial conditions at certain time, backward in time.
Can I ask a question here?
Oh, yeah, sure.
Okay, so since this d theta divided by dn is 0, so why n is dependent on theta?
Yeah, as I said, so because you fix the final slice.
Okay.
Okay. So you integrate from 1 here to here. The initial time is q, yes?
Yes.
And the final time is qf of theta. So depending
so the
on
final time is dependent on theta.
Yeah. So that's why this is the most important point, and which is which happens in many different sort of models. Actually, this is in some sense very similar to a discovered model. I mean, in that case, this sort of dependence theta appears later after inflation. But anyway, the whole point is that the during inflation, this theta direction doesn't contribute anything to the evolution, but this dependence on theta will determine how the universe evolves after inflation. You see?
Oh, okay.
Okay.
Yeah.
So this is the reason why it's so important.
Okay. Thank you.
Mm-hmm. Okay. Yeah. So this is the reason why it's sort of computing the curvature perturbation from this data formalism so powerful, and at the same time clarify everything. So here, if you, for example, try to solve the perturbation equations along the trajectory, of course, you don't see anything, huh? Of course, in this coordinate. But in terms of the phi 1 and phi 2, if you go back, oops, no. If you go back to this original sort of equation motion and the solve, then depending on this function, maybe you have some fairly complicated sort of behavior, and you maybe get fooled by those complicated sort of expression. I mean, in this case, it's because it's all the equations are decoupled, it's almost trivial, but if it is coupled, you can get confused with the all these expressions, and then because when you write down the perturbation equations, the perturbation of the curvature perturbation will definitely evolve in time, and the evolution will be highly non-trivial. But so even at the linear order, and then you go to nonlinear, it becomes even much more complicated. But if you write down everything in terms of the delta n, you immediately see in those cases, essentially what is important is the final condition, which and then dependence of this final condition. Okay, given the final condition, how this change of the initial condition changes the number of e-fold is the most important sort of quantity you have to compute. Okay. Right. So
Okay, yeah.
now, yes.
Okay. So that means that for the given final condition, the related initial condition is very important.
Right. Yes. So essentially, if you can draw these trajectories, then to write down how this n equals constant line would be drawn in this sort of in this case two-dimensional a space is the most important thing.
Oh yeah. That's clear. Okay.
Yeah. Okay. Right. And of course, and because the final point is fixed, then this n equal constant sort of hypersurface is not locally determined. You can only determine by integrating the equation. Okay, so that's the very important point. This n dependence cannot be determined locally. Locally, it's just this. Locally, it's just in each number of e-folds, you have the exactly same sort of evolution behavior independent of theta. That's the only thing you would see. So, but depending on the final condition, the total number of e-folds would be different depending on the theta, and which is the most important sort of dependence, which determines the final amplitude of the curvature perturbation. Okay. Right. Okay. So as I said, I mean, for the simplest exponential potential, you can easily kind of solve everything, and then you can define this Q. Q is essentially this sum of exponential functions. Then number of e-fold can be written in terms of the original field, which is like this, and the remaining is just some a simple model, which I mean, you can consider any type of model of potential, but for example, in this so-called multiple hybrid type inflation with two different fields, so you can assume, for example, the inflation ends at some hypersurface given by this G1 square, G1, G2 are some arbitrary constant. Equal some sphere on which depends on phi 1 and phi 2, and of course this can be realized by this hybrid inflation type potential. If you, as I said, includes a chi field, and this gives you that chi becomes sorry. Oh yes, this chi when this term becomes this sigma 1, then this potential of the chi becomes unstable, and the chi quickly goes to sigma square over lambda, and the inflation ends. So this is how the things you can actually realize this case. Then this would be the end of inflation condition. So so if you parameterize this end of inflation in terms of this amplitude sigma and in direction and cosine theta, cosine gamma, and sine gamma, for example, then you can immediately write it down the constant motion. This is just so it's cos theta divided by sine theta, something like this, and which is given in this form. So this is exactly what I'm just writing this everything down, and you have this explicit form of this in terms of the original scale field Q phi 1 and phi 2. So then you can easily obtain this number of e-fold for a given initial value of phi 1 and phi 2. So which is given like this. So it's you understand. So in this way you solve for the number of e-folds. Okay. Right. And then once you solve this, then it's very easy to do this expansion. This is just albeit some complications of the functions. It's just a Taylor expansion. And for example, if you can just expand to second, sorry, no, what is this? Oh, yeah. Well, this is just small notes on the end of inflation condition, because the end of inflation, if you assume this end of inflation condition, then there is a small difference in the energy density of the inflation depending on this this gamma. But if this difference is almost negligible, then you can compute the fluctuations number from this fluctuation expression, but you can essentially forget about this correction term. And I'm just trying to say that for given the parameters of potentials, that actually you can make it small enough. But this is just a comment which probably is not so illuminating, so forget about this. Anyway, so going back to this expression, which I, again, so you just focus on this expression, take the and expand this in terms of the fluctuation phi 1 and phi 2. And if you go up to the equation phi 2, then you obtain this expression. And so the leading order term will give rise to the sort of essentially the Gaussian fluctuation part, and the second will give you the non-Gaussian corrections. And of course, you can expand to a higher order non-Gaussianity and so on and so forth. Anyway, if you assume this delta phi 1 and the delta phi 2 fluctuation is just simply given by the h over 2 pi, which is the standard sort of case for, say, canonical scalar field fluctuations, vacuum fluctuations during inflation, then you can immediately write down the power spectrum of this fluctuation because you just square these coefficients and the sum of them and multiply by the fluctuation amplitude of delta phi and delta phi 2. And then the spectrum index is very easy to compute, which it turns out to be this 1 minus m1 square plus m2 square. M1 and M2 are essentially these sort of a mass scale appearing in the exponential function. Everything is in Planck units, by the way. So this must be small enough. So the smallness tells you that you have, oh, by the way, minus sign means that in this model, essentially you have a red tilted sort of a result spectral index. And you can compute tensor to scale ratio, which can be tuned to any value you want, and depending on this parameters gamma and so on and so forth, and so on and so forth. Okay, so by the way, so in this is the two-component kind of a hybrid inflation model. But if you assume it is a single component, then essentially everything reduced to this very simple formula. That's n is just a proportional to initial value of I minus the final value, which is just fixed some value divided by m, and this what is this? The spectrum index is just 1 minus m squared, and is tensor to scale ratio is 8 times m squared. And in this case, essentially, the single field case, you find that the local so-called non-Gaussianity computed in this way, because this is linear, as you could see, essentially 0. Okay, so compared to this case, I mean, as soon as you introduce another field and they gives some non-trivial condition for the end of inflation, given, for example, like expressed like this, then you find immediately highly sort of a non-trivial result, and everything can I mean, to be tuned to whatever the value you want to obtain. So in that sense, this is not so I'd say predictable. I mean, you essentially lose. You can you lose predictability in some sense, or you may say that you need more tests, more experimental observational quantities to test those say multi-field models. Anyway, so this I think maybe I shouldn't spend too much time on this, but anyway, the whole point is that they don't just forget about any details. It's whole point is here, apart from the fact that this non-local non-Gaussianity represented by the so-called FNL local. Local simply means that it's just if you write down delta n, it's just a Gaussian part plus some Gaussian square part plus with the coefficient which is independent of any coordinates or anything. So this means that the Gaussian is local in the sense that if you write down the say single point, say distribution function, a statistical distribution function, then this deforms the distribution at each local point. Anyway, apart from the fact this is positive, as you could say in this specific model, it's always positive. But apart from, sorry, so no, I may be wrong. Yeah, actually, you may have some possibility to have this denominator to be negative. So actually, so I'm sorry, I was wrong. So you can actually produce any non-Gaussianity you want. Oops, but I say it's positive. So maybe there's a condition on positivity. But anyway, this is just a matter of model. So forget about this for the moment. And this is just some model which I enjoyed by choosing some particular values. And you can always choose parameters to make it consistent with the observations and so on and so forth. And for example, you can make this non-local, FNL, non-Gaussianity, a parameter to be about 5 to 10, which is still acceptable from the current observation. In other words, that if you find this to be about this value in the near future, then it has an indication that you are actually having two field models. Okay. Yeah, so far is okay. This is just, example, but the whole important point was this. This was the essence of the delta n. Any questions? Okay. Okay. Maybe you can ask me questions at any time later. So apart from this simple model, another fairly simple but very interesting model is this so-called ultra slow roll model of inflation. In this case, in the simplest case, you just simply assume that potential is given by a constant. That is just a cosmological constant. So essentially the universe is dominated by cosmological constant, but the scalar field rolls slightly in some sense, but not by the potential force, because derivative potential is 0. So in the leading order, you say that the actually slow roll solution is a phi equal constant. It just stays at certain point. The actual motion of phi is dominated by so-called decaying mode, because if you put this equal to 0, you immediately see that the phi dot is proportional to a exponential, so 1 over a cube, right? This just this shows yes, the phi dot is proportional to 1 over a cube. And if h is constant, this can be easily integrated, and you get the result or some constant of integration plus a term which exponentially decay. Yes. Okay. So which means actually the this value of phi is does not by itself determine the number of folds the evolution of the universe. Both the value of phi naught, phi 0, this constant, plus this decaying components to information. 2 degrees of information is necessary to solve the background equation, right? So in general, this solution dominates, and this is moving slowly, and this just goes out. So in general, in the slow roll case, you have only single degrees of freedom, and which is the slow roll equation motion, in which case the phi dot is determined by this leading order slow roll solution. But in this limit, when the potential is completely flat, then this decaying mode actually becomes highly non-trivial. It gives non-trivial contribution to the equation of motion. So, in some sense, you could say this is ultra slow, means slower than slow roll. But actually, it's a bit misleading. Anyway, to say this, but in any case, the whole point is that so you cannot ignore this decaying mode, which means that the number of efforts, if you write down in terms of scalar field, they will not be just a function of phi, but will be a function of phi and phi dot, meaning that as actual phase space of the scalar field phase space becomes important rather than just the configuration space. Okay, but even in this case, if you just know this, the fact that how the number of efforts depends on phi and phi dot, you can easily compute delta N and compute, say, a non-Gaussianity and so on and so forth. And this is the one example. So let's apply this delta in formula. So you assume that at certain point inflation ends, and because the potential is completely flat. Oops, takes some time. Sorry, completely flat. You have the translation invariance of phi. So for simplicity, just set the end of inflation to be phi equals 0. This is okay, huh? Then you can find a general solution that the phi is from the n. This n again, n is the number of efforts counted backwards in time. So when n equals 0, phi equals 0. Okay, and when n is large means that you go back in time, then you increase the phi into, in this case, negative phi direction. And phi dot is given by this. Also, phi dot increases is like exponential if you go back in time. Anyway, so you have these two solutions. And given these two solutions, of course, you can easily find, I mean, from here that you sort of, how to say, remove phi naught to have obtain the expression of n in terms of phi dot and phi. So this will be just a number v4 is given by a function phi and phi dot, which is given by this formula. Now, once you are given this formula, it's very easy to just compute again the curvature perturbation. The only difference is that now you have this delta phi dot term too. So you have to compute, you know, this the first and second derivative and so on and so forth. But the important point is that although this phi dot dependence is very, very important, we know delta phi dot is almost zero outside the horizon. It's essentially a negligible because phi freezes out, which means actually at leading order, delta phi dot can be just taken to be zero. So it's important to take this phi dot dependence into account, but after you take that into account as an independent variable, you expand this expression to arbitrary order of your interest, you can just put delta phi dot equal to zero. So you end up with this this expression. Okay, end up with this expression. This delta phi dot will be all becomes zero. And this is a very important point. I mean, and delta phi has the standard sort of fluctuation of h over 2 pi. So in the end, you obtain this expression. By the way, this you can easily see that this from the equation of motion, 3h5 plus phi dot square is just a constant, and this constant essentially is a parameter of the model. But since number of V4 is nothing to do with virtually nothing to do with it, it doesn't explicitly appear in those expressions. But anyway, but when you do compute, then you can immediately see that this is just phi naught, and this is phi naught square, and so on and so forth. Anyway, and it's very, very easy to compute the power spectrum, and the power spectrum is just given by this h over 2 pi naught square, and in this special case, you have the exact scale invariant spectrum. Essentially, apart from the very, very minor correction, it's almost exactly n equal 1. And then non-Gaussianity is non-vanishing, although this is a single field, single inflation model, because you have the phi dot dependence in number of V4s, this so-called local non-Gaussianity will not be zero, but it has some finite value. And this can be extended towards arbitrarily a more complicated models where you can produce some arbitrary non-Gaussianity and so on and so forth again. But anyway, and you can choose this to fit to the observational result at the present, although it doesn't say that it doesn't support this model, but I'm just saying that so you may have this kind of model. So this is one example that when you have non-trivial phi dot dependence in the number of V4, then even in a single field case, you may have some result which is different from what is known for standard single field slow roll inflation. Okay. Any questions so far? Please just let me know anything, any think.
Could you turn to page 51, please?
Yes,
Okay.
please.
Okay, so I can see the equation of motion, that is phi equals to phi 0 times one minus e to the 3n. So to my intuitive is that I can just write n as a function of phi. Why I need to write phi dot here?
Yeah, well, as I said, I mean, once you fix the final phi f, then well, we want to know how the n depends on initial conditions. Huh? So you have to express n in terms of phi and phi dot, because the phi alone does not depend. Then you have this additional parameter coming into play.
Yeah.
But you want to know n as a function of phi and phi dot, and this is exactly what I'm doing. Yes. Then if you just use these two equations to write down this number v4, then it can be.
That's correct, of course, but I think that if I just write n as a function of phi, that means I will introduce this parameter phi 0.
Yeah,
So,
but what is it then? What is it? I mean, it's it's just you know as you can see, it just depends on the say where you put this t equals 0, t0 is. I mean, you know, it doesn't mean much, right?
so that means the phi 0 is arbitrary, it's not physical.
Well, no. That's why I'm saying it's just yes, model. I mean, yes. Well, you can choose whatever the value you want to choose, apart from maybe phi not equals 0. Yes. The only condition is that phi dot decays like yes. This is the only yes condition, huh? And this phi 1 is arbitrary, right?
Yes.
Yeah. So you see, it's just maybe depend on at which moment you start to measure this decaying mode. Yeah. So everything. I mean, so this just in some sense initial amplitude determine the initial amplitude, but it's just free parameter which is not determined from the theory.
Yeah.
Yeah, so you don't want to have it in this. Well, of course, maybe you can replace this dependence on phi dot by dependence of phi not. I mean, that may be possible, but in any case, you do have 2 degrees of freedom.
Yeah.
That's the whole point. That's the most important. This, actually, you're right. If you just write this n in terms of the phi and phi 0. Then you have the only thing is that you just have to understand how to compute the fluctuation delta phi 0.
So that's not physical. Okay.
But that's what means. But it's much easier and in terms of to express this in terms of phi and phi dot, so that you know how to compute the number of v4s given the initial conditions of phi and phi dot, right?
Yeah, right. So the most important thing here is the degrees of freedom.
Yeah, that's right. The degrees of freedom in the system. If
also,
yes, please.
Also, I'm also wondering one thing, that when we compute the non-Gaussianity parameter in delta n formalism, that means we can only calculate the nonlinear evolution outside of the horizon.
Yeah, that's right. That's right.
So if the 3-point correlation function have some non-trivial properties inside the horizon, how can we deal with this?
Oh, it's simple. I mean, you just when you for example, when you from here, when you compute the let's say the 3-point function, yes, you compute the 3-point function, this the delta n, right?
Yes.
Then you will have a delta phi, and that will be non-vanishing if this has the non-trivial 3-point function.
my idea is that for the 3-point function inside the horizon, it has been.
Well, they included this fluctuation delta phi.
Okay.
You see?
Yeah.
Is that clear? Yes. I mean, so for example, if you take a correlation function of delta n, maybe not, it's not so easy to write. Let me see. Oh, maybe I just write it. Okay, so instead of delta n, I say dn. Say maybe dn1 and dn2, dn3, 3. Yes, as if you want to compute this, then it will automatically contain this. It's not equal. It's proportional to this. It's some term which is d phi. Let's say df, df1, df2, df3. Yes.
Yes.
Right. So plus dot. And usually, if this is this fluctuation in the scalar field is Gaussian, then this just vanishes, right?
Yeah.
But if it is not, then you have the intrinsic 3-point function, which appears in the final result. So this 3-point function must be computed inside the horizon. But but not but yes. But inside the horizon, you can essentially ignore the gravity. So it's just essentially some interacting scalar field computation. So which is not too difficult. I mean,
that's much more complicated, I think.
Well, it's slightly,
that
but
means we need
not much.
to expand the action to the
yeah. So
modern,
this is what the usual people do. Huh? You use so-called informalism or something, yeah. But
yes.
anyway, in this formulation, you don't have to in those in formulation, people try to compute this left-hand side directly, using some variable of this curvature perturbation. But that's a kind of waste of time and thing, because all these contribution from outside the horizon can be very simply given in terms of this curvature, the delta n form. So
Yes,
this means inside the horizon, you just ignore completely at leading. I mean, unless you have very, very complicated scalar field model, maybe that's not the case. But in most cases, you can just completely ignore the effect of gravity. Yes, I mean, you just assume this scalar field lives in some expanding the background and interacting. And then you just use the standard sort of interaction picture and compute this 3-point function for scalar field. Sorry, so for this thing. So you see, you can divide the sort of computation into 2 parts, and the one part without any gravity, and it simply just expand the action Lagrangian into the non-linear order of delta phi. Yes, inside the horizon, and then just compute the outside the horizon. You don't compute anything. You just compute delta n.
Okay, very clear.
Yes, clear. Okay, thank you.
Fine.
Excuse me, I have another question for the
Sure.
previous slide.
Okay.
So besides the
these slides are before
the previous slides.
This one.
Yes.
Yeah.
So besides the degree of freedom of phi1 and 0, phi 0 and t0, do we have freedom to choose the phi f to be 0? I mean, if I choose another value for the phi f, do we have the same result?
No, yeah, but because as I said, in this particular, well, of course, in general, it's not. In general, it will have some dependence, but since I have explicitly, I've considered the exactly flat model of potential. This model has complete a so-called shift symmetry, huh?
Okay.
You see, changing phi to phi plus some constant doesn't change anything. So,
Okay.
so the constant term actually doesn't mean much. Yeah, the most important. Yeah, well, it's not so easy to see this, but you see the point?
Yes, I think so.
Yeah. So this is putting this is just the you do some use this shift symmetry of the background, the scalar field. So you can do this, yes, all the time. In
Okay.
this model, in this particular model.
Okay.
Oh, of course. Sorry. So, of course, this means that you are cutting this potential at certain moment, at a certain point, so that the inflation ends. You cannot have this potential forever. Then the inflation just keep continuing. You have to end the inflation. So you just want some this inflation to end. And then what I'm trying to say is that you can choose the end point of inflation to be phi equals 0. That's all.
I see.
Yeah, there's not much more. Yes. So,
Yeah.
so this, yeah, in this.
Yeah, I see. So,
Yeah.
so you have the shift symmetry, so I can redefine the phi to be phi minus phi f in the Lagrangian. So you
That's
always
right.
have,
That's right. That's
yeah,
right. Everything,
okay.
yes, the same. Yeah. Okay.
Okay.
Anything anymore?
I have a question. So
Yeah.
I think it's related a question in the morning session, that time formalism in the momentum space. So about the non-Gaussianity, can you calculate the non-Gaussianity other shape of the triangle using the time formalism other than local?
No. So as I told you when I explained the how to compute, say, 3-point function and so on, those this because this point these are essentially just function of space, huh? Well, essentially at the leading order, there is a background quantity. This is just a function of space at a given time, huh? Yep. Which is, in our case, it is flat slicing. So since the coefficient is just a function of time, or maybe you could say that so in that sense, apart from the spatial dependence, it's just a constant. So this is why it is called local. Yes, fluctuations are all local, and any sort of a non-local or say a non-Gaussianity should be contained in this delta phi itself.
Right.
So in that sense, when you want to compute some non-Gaussianity away from this local non-Gaussianity, then you have to go inside the horizon, because outside the horizon you can never have a non-local interaction, because that will be in contradiction with causality. Okay, so all the causal interaction which produces some non-local 3-point function must be effective only inside the horizon.
Oh, I see.
Yeah, so that's why when you want to compute this delta phi, and it's a statistical nature, then you have to compute everything inside the horizon. But as I said, inside the horizon, a computation you can just completely ignore gravity, so computation becomes simpler.
Okay, thank you.
So it's essentially the standard sort of quantum field theory computation. Okay.
Yeah.
Any other questions? It's okay. All right. Anyway, yeah, you can ask me other questions at any time. Now, let me maybe I don't have enough time to go through all of them, but maybe I should just make some small comments on this conformal frame independence. And this is especially may be important because now people talk about all these modified gravity theories, and depending on your model of gravity, of course, you may have completely different frames in which the gravity is expressed. For example, there may be an Einstein frame where the gravitational action is solely in terms of Einstein action, but you have some very non-trivial coupling in the between the metric and the scalar field. You may have some so-called Jordan frame where the matter field is minimally coupled to metric, but the coupling of there is some non-trivial kind of scalar gravity part, scalar field, which deforms the Einstein action, and so on and so forth. So now question arises whether this delta n, which is supposed, we assume that this is the final curvature perturbation in the adiabatic limit, and if this is gives the initial condition for the, say, later evolution of the universe, and in which sense that if this has the amplitude of that such a perturbation has some physical implications or physical meaning, then if it depends on the frame, then we lose the basis of those computations. So it should be independent, but how can we show this? So this is the kind of question you can pose, and what you find essentially. Here I'm just explaining the sort of some typical cases of the scalar tensor theory. So in the so-called Jordan or Jordan-Brans-Dicke frame, you have some scalar field couples to this rich scalar curvature, which represent the gravitational degrees of freedom, and because this contains second order derivative, actually this gives rise to some non-trivial second derivative of the scalar field. So scalar field is intrinsically, this scalar field is coupled to gravity. So in that sense, this is not simple tensor theory of gravity, but scalar tensor theory of gravity. But the Lagrangian, so this is the gravitational part of Lagrangian. The matter part is assumed to be minimally coupled to some this metric, which gives rise to this curvature. So this is the kind of standard assumption. I mean, of course, so the very strong assumption, which is, we hope, I mean, not maybe we hope, we think it is usually correct, is that the coupling of all the scalar, so matter field is universal with the metric. If they are not universal, then the things get really messy, and so that is the something you have to deal with carefully. But for the moment, we assume this is universal, and from a experimental point of view, at least for baryons, there are several sort of those equivalence principle tests, and it says that they are independent of the charge or the baryon number and so on and so forth. It seems that everything is coupled universally, at least in as far as the matter contents we know, standard model matter contents are concerned. Now, if you assume this to be universal coupling, then maybe it doesn't have to. But if you have assumed that gravitational part of the action is like this form, then you can make the so-called conformal transformation to make this the scalar curvature term, coefficient of scalar curvature term to be a constant. But instead, you have a very non-trivial potential, the scalar field Lagrangian, and at the same time, because of this conformal transformation, you will have some coupling of this scalar field to the matter Lagrangian. Again, this is usually a universal if you assume the universality in this Jordan frame. But of course, if this universality is lost, and then you may have some different sort of depending on the matter field, you may have different coupling to this kind of a scalar gravity scalar field. Anyway, so these two are sort of a most sort of a typical example of different frames, and if you do this transformation, then you have this all everything transformed like this. Oh, by the way, maybe I should have shown this before, huh? Before this Jordan frame and Einstein frame. So, for example, if you start from here, and then you can, if you identify this f with omega minus square, then the resulting sort of a space will have some rich scalar, which is simply given by this formula, for example. But this is just a sort of a standard thing. Maybe I don't actually need to write it down. Anyway, the whole point now is let's just consider the cosmological perturbations, and then if you write the now I'm focusing on linear perturbation. That if you write the, for example, consider the tensor type perturbation, which is just perturbation which appears in this spatial component and which is transverse and traceless, then if you use the conformal time, then you can extract everything in terms of this conformal time, and sorry, conformal factor, which is just represented standard scale factor. But apparently, at this level, since well, once you take this conformal factor out of this metric, then this so-called conformal time is definitely, by definition, invariant under conformal transformation. As you could see that if you do some conformal transformation, it just affects the total sort of a scale factor component and never affect this place, the remaining sort of in some sense, conformal metric. So this means that the definition of the transverse traceless tensor perturbation is conformal frame independent. So once you can, if you can evaluate this fluctuations in, say, tensor type perturbations in one frame, then you should have exactly the same result for the other frame. Of course, because the change in some non-trivial sort of factor and so on, maybe the meaning of the coordinate may change, but as long as you choose your coordinate to express everything in terms of this eta and x, then you see this is completely independent from any prefactor. So tensor perturbation is definitely conformal invariant. Vector perturbation, you have some vector which can appear in, say, this shift vector component and the kind of a anisotropic part of the spatial metric, and the vector by definition is that the transfer, it has a transverse condition, so you essentially have 2 degrees of freedom. Anyway, again, if you do the conformal transformation, this is again omega conformal frame independent. So this means that the tensor and vector perturbations are conformal frame independent. So you don't have to worry too much about anything as long as the tensor and vectors are concerned. As for the scalar perturbation, it's not exactly the case, as now you could see that in the scale case, the scalar perturbations, if you write in this in the conformal time space-time form, you have the Raph's function, shift vector, and the curvature perturbation plus some anisotropic component of the spatial metric, and then if you do the transformations, then you find actually this B and E, because it contains some derivatives, they in a spatial argument, these are omega independent, but A and Korea won't be, because this omega in general was contain perturbations, and then if you expand that around some a background, then this will have a contribution. As this is said, omega will have some background value plus some non-trivial space-time dependent component. And if you include that into this right-hand side to define the sort of a perturbation in this conformally transformed frame, then a lapse function and this curvature perturbation will have a shift. So they are not invariant. So this is sort of a source of potential problem, because we are interested in the curvature, scalar curvature perturbation. Huh? But now that's the important, here the important point is this so-called adiabatic limit kind of thing. Now, if you assume our universe is dominated by some scalar field, and so that the scalar field is the source of all this curvature perturbation, and which defines the this conformal frame, conformal transformation. This is the case if this single scalar field is the source of all the curvature perturbation and everything. So in that sense, that essentially you have the single scalar field system. Then this curvature perturbation on comoving frame, which is defined essentially in a gauge invariant manner at the linear order. Maybe I haven't said this shown formula, but there's some formula like this, which is again invariant under the choice of coordinates. So if you sorry, wait. Right. So if you write in this form, wait a minute. Oh yeah, yes. This as I said, is if phi fixes everything in the background, this h over phi dot can be just written in like some logarithmic derivative, not the other way. The derivative of phi of the log of a. It's okay. I think it's clear. Hopefully, yes. Anyway. So this is or d phi dn or dn d phi. Oh yeah, dn d phi is okay. Huh? That's what we used in the when we talked about the delta n formula. So this is essentially the coefficient of the delta n. But anyway, since this curvature perturbation defined on the frame where the delta phi is 0, and which coincides the curvature perturbation we want to compute. Actually, it doesn't really matter in which frame you evaluate the scale factor or number of efforts or something, because in this uniform delta phi hypersurface, this vanishes anyway. For example, for scalar tensor theory, which as I said is some function. This is the Lagrangian for phi, and which couples to scale a curvature like this. Then you have this. You can transform this into the Einstein frame with some function omega, which is given in terms of this function f. Then in this Einstein frame, you can compute the curvature perturbation, but this curvature perturbation, of course, is computed in delta phi equals 0. So therefore, essentially, omega is just a function of time, and it doesn't contain additional perturbation. Therefore, this is invariant under the conformal transformation. So this tells you, of course, this is in the case when you have the single field which governs everything. But essentially, the adiabatic limit means that you have only single degrees of freedom which is controlling the evolution of the universe. So once such a stage is achieved, then, and which is the case when which is that what exactly you want to compute when you compute when you use the delta n formalism. So the curvature perturbation actually is conformal frame independent. Okay. So actually this can be fairly easily generalized to nonlinear case, and I don't think I have enough time to do the details, but you could sort of easily expect that you, with the definition of the curvature perturbation, as we have done in standard case, a nonlinear curvature perturbation will be defined for nonlinear perturbations, and the final result will be independent of the frames if you take the adiabatic limit. Okay, I guess so. This is the summary. Delta n formalism is a powerful tool to evaluate curvature perturbation from imitation, and especially in case of multi-field case, or maybe this non-slow roll case. And the another important point is that the official when you, apart from the how to evaluate the fluctuations of the delta phi itself, delta n formalism doesn't really use the background sort of equations. So in some sense, well, essentially you may have some, let's say, modified Friedman equation or something, but if this modification is such that essentially you have a very similar sort of a case, for example, the H square is essentially determined by density alone and so on in the early universe and so on. So in such case, all the discussions I have done for the general relativity can be applied to all this theory of gravity, other theories of gravity, and which can also result in this nonlinear generalization. Again, when you write down all this nonlinear case, I didn't use the theory except for the this energy momentum conservation law. So again, it's in the adiabatic limit, you know, independent of theory of gravity or anything, you can formulate delta n formalism, and which is very useful in evaluating non-Gaussianity and so on and so forth. And yes, as I said, it can be applied to some non-slow roll model of inflation. And finally, I showed, I didn't really show, but I explained that actually delta n can be computed in any frame, any independent of conformal frames. So that's, I think, the end, perhaps. Yes. Okay. Sorry, in the end, maybe I went too fast. I hope it was not too bad. Any questions, please?
Hello, may I have a
Sure.
question?
Yeah.
This is just out of my curiosity, but I'm wondering about the so-called disconformal transformation.
Right.
So that means that the transformation of the metric involves the kinetic
Right.
so the matter field. So can we define even such a transformation? Can we define the gauge invariant quantity just as the same as what you've done?
I do. I think there may be some work done by some. Is there anybody know this? I mean, probably there must be some work on this, huh? I haven't really looked into literature, but yeah, I'm pretty sure. Yes, I mean, if it is just simple sort of a transformation, Yeah. Yes. It shouldn't change the result. That's
I see.
yeah.
I see. Thank you.
Yeah. Maybe somebody knows a reference. Yeah. Anything else?
Can you emphasize or kind of comment a little bit more on this adiabaticity in the third point? Yeah, why this adiabatic condition is so important?
Right. So now, just a minute. Maybe I should stop first and can I? Just a minute. Sorry. Okay. So this then let me share the screen again. Okay. So if you go back to the very beginning, where is it? Here it is. Okay. So this is the whole point in some sense. What we can compute actually is the some fluctuations at the end. I mean, when after that, all the evolution is uniform. Okay, so this is exactly what you can compute. I mean, in some sense, if you have still some isocurvature a component in this time, then you can of course define delta n, but it's not so useful unless you know how the evolution, how the universe evolves afterwards. This is exactly like this. Let's assume that our universe is current stage right here. Yes, not current, but maybe at some certain point in the early universe, but not too early in the universe. And you have some isocurvature sort of a difference, and there are some isocurvature perturbations in the universe. Then you may compute some say a curvature perturbation. Let's say at this slice you compute curvature perturbation, huh? But this amplitude of curvature perturbation you computed at this slice is nothing to do with this final curvature perturbation you want to compute. Yes, it's nothing. There's no difference, no relation unless you define how the for example this isocurvature perturbation transformed into the curvature perturbation. You see the point?
Yes. So yeah. the key point is that in the final slice you calculated the curvature perturbation by the delta formalism. You have to make sure that there is no isocurvature perturbation. That's the
right.
key point. Yeah.
No, you may have isocurvature, but it's that isocurvature, but make sure this isocurvature perturbation will not generate new curvature perturbation, additional or maybe to replace the curvature perturbation you have computed, right? This is the, for example, in the case, this is exactly the case of this oops, it's again, oh no, so I should stop this and where is the model Carverton? Yes, Carverton model, yeah. In this case, well, of course, in this case, because you have given some a specific model, so you know what is going on. But unless you define this end of, say, a Carverton-dominated stage, or at the end of this matter a stage where the Carverton behaves like matter, knowing this quantity doesn't help much, doesn't determine the final curvature perturbation at all. It's nothing to do with this, right?
Okay.
Yeah, so you need this condition. This condition is essential, which means that how the universe ends up with some adiabatic universe. And as soon as you fix that condition, then this meaning of the curvature perturbation becomes real. But before that, the amplitude of this or this doesn't mean anything. I mean, you can compute that, but it doesn't affect any physics. Any physics which we observe today, unless you fix this condition. Okay?
Okay.
So you mean the diabatic limit is satisfied on the final slice, and that's enough?
Enough, of course. I mean, if the universe is in the diabatic limit by that time, then beyond that point, nothing, no subdominant component with becomes important.
Yes,
and so on,
yes,
so forth. Yeah.
yes. Okay.
Right. So this is very, very essential. Otherwise, you can, in some sense, always hide a bomb. For example, you can consider some universe which has a very, very small, let's say, this caviton-like component in the universe, and which has huge fluctuations, but which is hidden inside in the universe. In the very, very early stage where the density of this this caviton is completely ignorable. Yes, but if they start to dominate, or if any of the fluctuations or the amplitude of the say density, it becomes non-negligible, then, and if they have a large fluctuations, then all the fluctuation amplitude you measure today should be determined by this component. And then anything you computed for this other component becomes meaningless. So that's why you need a diabatic limit.
Okay.
So any other questions?
I have a naive question.
Sure, please.
So can I use this dead end formalism to calculate the perturbation of some scalar field phi, not during inflation, but during some radiation dominates or matter dominates, as long as the phi is subdominant?
So sorry. What kind of situation you want to consider again?
I mean, can I use this dead end formalism to calculate the perturbation of some scalar field phi, but not during inflation, but during radiation or matter domain error, where the phi is subdominated?
Wait. Why it must be subdominant again? You mean that so you may have some non-trivial scalar field, but so again, if that scalar field is completely subdominant, then essentially you have to how should I say? So if it doesn't affect the number of e-fold at all, then by definition, it means that it never contribute to the curvature perturbation. So at certain point, that influence, affect, that should, this delta phi should, the fluctuate, or the scalar field, whatever, should affect the total energy density of the universe somehow. So that's an assumption. I mean, that's something you need. Otherwise, if it is completely subdominant all the time, you can never give any influence to the curvature perturbation, right?
Yes.
I think what Sojian said is kind of like a curvature scenario, but with the kind of negligible energy density compared to the background radiation. Like R is very small, something like that, right?
Oh yeah. Okay. Wait. I'm so.
The energy density of the curvature is negligible, but the curvature perturbation is mainly transferred from this curvature.
Yeah. Okay. So in this sense, this maybe this picture is much easier, better, huh? I mean, so as I said, well, let's say this theta direction is like a curvature direction, whatever you call. I don't know. I mean, it's some scalar field, and in this specific case, it's completely. I mean, if you assume this is a field, then the energy density towards this direction is 0, right? In the background. You understand? Yes. This is just purely isocurvature. Yeah. But if they somehow decides the future of the universe like this, in this case, this parameter, sort of a isocurvature field, the value of this determines how the dominant component of the energy density behaves in the end, after, let's say, some phase transition or something. Then, yes, this is the information of this theta is very important, as we have just shown this. And including that information in the number V4, then of course you can compute the delta n. Yes.
Okay, thank you.
Yes, is that okay?
But in that case, the inhomogeneity is generated during the radiation dominated universe does not cross the horizon. I mean, does not exit the horizon, right?
No. So I'm assuming all the scales is outside the horizon. Yes. So all the scales is long wavelengths. So this when it comes inside the horizon, of course, all this delta n computation is meaningless. You have to do some local computation, which is much more complicated in the in the phase during the phase transition and so on and so forth. Maybe you're good at it, but I don't know. But as far as this, this field, say homogeneous sort of component in say each Hubble patch is concerned, then you have this kind of dependence, right? For example, this not completely subdominant scalar field, let's say theta, depending on the value of this theta, that the phase transition temperature is determined or something, huh? If you have that kind of a situation, then even during the radiation dominance, you have some phase transition and of the dominant matter field, yes, or maybe the field which start to dominate in later stage. Anyway, so this phase transition, how and when it makes transition, will depends on this theta. Then the value of theta is a very, very important quantity. And if there is any fluctuation in theta, that will produce a non-trivial curvature perturbation, right?
Okay.
Yeah. So this is what I call the bomb. You can just hide a bomb in some parameter theta. And depending on how you expose that into reality, through some phase transition, sorry, you may have completely different sort of universe. And in this case, any fluctuations in, say, this longitudinal direction or this standard sort of a curvature perturbation along the trajectory will become completely subdominant. Huh? Everything should be determined by theta.
Any other questions?
Hello, I have another question.
Yeah.
In the context of the cosmological collider, as far as I know, they are trying to calculate the non-Gaussianity induced by higher dimensional operators, including infraton. And such a higher dimensional operator doesn't contribute to the infraton potential itself. It seems that it doesn't change the n during inflation, but I wonder how can we calculate this 3-point function in terms of this within this data and formalism.
Yeah, well, so as I said, I mean, maybe there are cases which I don't really know. You know, the cases where the gravitational interaction is very important inside the horizon. In that case, you do have to take this correction into account. But in any case, the simplest and most intuitive way to compute those the non-Gaussianity or non-trivial effect is to choose so-called flat slicing, where you minimize the effect of gravity or the deformation of the geometry, and then compute this interaction, compute everything in the standard interaction picture in scalar field. Not in some curvature perturbation variable or anything, because those are not really a good, intuitive variables inside the horizon. Inside the horizon, the scalar field is something we know. In daily life, we talk about the Higgs field and so on and so forth. So we know everything. So if you compute in this way, and then you have, as I said, you will obtain the sorry. Yes, the property of this is the phi, huh? And then of course in general this not in general. So commonly you just assume these to be Gaussian, but you compute with this higher dimensional operator or anything, then you have some non-trivial correlation between this scalar field, and that automatically gives you, all the non-Gaussianity you want. But this will give you additional information about how these sort of in multi-component the field space a scalar field evolves outside the horizon, and which can be highly non-trivial, and to compute such in this sort of in formalism interaction picture is just a waste of time, and everything's so messy. Yeah. So, yeah, that's the whole point. Yes.
I see. Thank you.
Yep.
So any other questions or comments? Or
excuse me.
now all happy? Oh yes, please.
Yeah, somebody. Yeah.
As you probably know, there is a so-called stochastic delta N formalism, and I have just started to worry about something. There people assume inflaton field phi takes some specific value at fictitious initial time, and they investigate the first passage time to the field value where inflation ends, but that is technically e-fold from the uniform density slice to the uniform density slice, so it's not from flat slicing, but their results seems reasonable and successful. So I'm wondering why that goes well.
Sorry, I maybe I don't know much about this. It's essential. What I and usually, sorry, what should I say? Okay, so what I understand usually is that actually you may officially write down this kind of sort of a formula where you have the background from fluctuations, yes, and which gives you, say, the number of and so on and so forth. But if in the case when this background is not very well defined, in the sense that the evolution is dominated by fluctuation itself,
yes,
then this meaning of number of people should be carefully defined. So I'm not exactly sure about exactly how you should define and so on and so forth, but there must be some way, yes, at least maybe on scale slightly greater than the horizon, something you define some smooth field or smooth kind of a semi-classical or classical universe, and define how this version of the universe is affected by these quantum vacuum fluctuations. And so if you do the similar, this kind of a formulation, and if you write down the let's say the probability distribution function of n, then yes, in the end you may be able to just compute the this delta n, because now the only thing you have to do is just the well, it's maybe you just in the end you define some mean value of n, and then you take the deviation from this mean value, and of course this deviation will not be Gaussian distributed. It's a very highly non-Gaussian perhaps, and so so this kind of thing probably can be done, but I don't know. In practice, it's I'm not exactly sure what you mean by initial uniform density and the final uniform density and so on and so forth. It's I guess you do need some fluctuations in the initial slice.
Yeah. Yeah. I mean, in stochastic inflation,
Yeah.
the field value evolve according to some stochastic differential equation, which includes
I know. Yeah,
random.
yeah.
And
what I'm saying that you must have some delta phi in the beginning, no? What you don't?
Yeah, they don't take delta phi. They just assume some a specific value. They assume that field takes a specific value at the initial time.
No, but you said they use some kind of a stochastic equation, right?
Yes, right.
Then you have a source of stochasticity. What is it? This source of stochasticity is just delta phi.
Yeah, that's right. Yes.
Yeah. So they must have that. Yes. So I guess that's what they do. No.
Right, but I'm wondering that if that end they consider is really evolved from flat slicing. So maybe this question is a bit away from your talk itself. Sorry.
Well, I don't exactly know, but I have a suspicion that essentially, but when you formulate this everything, then again, it's if you try to include gravity, then things get really messy and it's not so easy to solve. So whether you assume it explicitly or implicitly, if you in some sense ignore this gravitational back reaction type things in the beginning, then essentially you are doing the same thing as doing on the flat slicing. You understand the point? So if you have just simple fluctuations in scalar field and you formulate some Fokker-Planck type equation, essentially it's formulating everything in flat slicing.
Yeah, so you mean they just neglect gravitational fluctuation part?
Gravitational back reaction in some sense, yes. It's usually suppressed by 1 over Planck mass squared. So so usually you can ignore that. You have some non-trivial scalar field dynamics.
Okay, thank you.
Yeah. Mm-hmm. Okay.
So probably you may accept one last question. So if everybody is happy with Misao's lectures and
Okay.
crystal clear, then okay, fine. Thank you, Misao, for nice lectures, and
You're
let's
very welcome.
give him very big upload over your screen. So thank you very
Okay.
much. Thank you.
Thank you. Yes.
Thank you.